All right, I'll take that as a no. All right, so last time we finished off talking about if you have a basis that you know something that you know is a basis for a vector space, and you've got another set of vectors in the vector space. If there's more vectors in the second set, which I've labeled T in the handouts here, if there's more vectors in the second set than what was in the basis, then you know guaranteed without a doubt that bigger set is linearly dependent. We went through the proof last time. We also notice in part B it says that if we have a smaller set of vectors than what's in the base, the thing that we know is the basis, then we also know that it cannot span. The proof is similar. I'm not going to spend the time, just to save some time, I'm not going to go through it. I'll just send out a handout. I'll send out an email later on to show you what the proof is. It's very, very similar. We did here, remember we wrote each of the vectors as a linear combination of these because we know that it was a basis, and then worked to get a contradiction of the fact that those vectors had to be linearly independent because we created a homogeneous system that had more unknowns than equations. And the proof is the same basic concept. To show that it doesn't span, you'll get the same contradiction. You just have to you go the other way around, assume that it does span, and then write each of the vectors in the basis in terms of the spanning set, and then you'll get a contradiction that way. Like I said, I'll just send out an email with that so I don't spend time on it in class. But the idea here is that I mentioned this last time, I'm going to mention it again. A basis for a vector space is the largest possible linearly independent set in the space, and it's the smallest possible spanning set of the space. Any other set that is also a basis then must have exactly the same number of vectors in it. And that's the whole point of this particular theorem, is that every single basis for a finite dimensional vector space must have the same number of vectors in it, which is what leads us to the next definition of what we mean by the dimension of a vector space. So the dimension of a vector space is just the size of any basis of V. Or I should say for V. The previous theorem tells us that all bases must have the same size. Because if we start with one basis, any set that's bigger can't be linearly independent. Any set that's smaller can't span. So if it's going to be both linearly independent and span, it has to have the same size as the basis that you already have. It doesn't have to be the same basis, it just doesn't have to have the same number of elements in them. All right, so there's one anomalous exception, if you will. We know that the vector all by itself, the zero vector, forms a vector space. It's the only vector space that has only one vector in it. Every other vector space has infinitely many vectors in it. But the vector space that's just the zero vector isn't very interesting. Okay? It has dimension 0. It's the one that has dimension 0, and it actually has an empty basis. That's the one anomalous exception. Everything else has vectors in the basis, and so we can count them. All right. So let's talk about these other ones. For Rn, what do you know for a fact is a basis for Rn? Remember we went through all those standard bases last time? What do we know for a fact is a basis for Rn? How about R3? Tell me what you know for a fact is a basis for R3. Yeah, 1 0 0 0 1 0 0 0 1, right? That's definitely a basis for R3. For Rn, we do the similar thing, right? We put a 1 in the first component, then all zeros for the rest. 1 in the second component, all zeros for the rest, and so on down the line. How many vectors are in it? How many vectors are in that set for the basis for Rn? N of them, right? So what's the dimension for Rn going to be? N. Good. What does Pn mean again? P sub n? Yeah, polynomials of degree n or less, right? And then including the zero polynomial. What forms the basis for Pn? What's our standard basis for Pn? What's that? Okay, so x to the n is one element of the n there. What else has to be in there? Yeah. Right, exactly. And remember, if we're going to generate an infinite degree polynomial, you have to generate the constant term, generate the x term, generate the x squared term, right? And so on up the line. So 1x, x squared, all the way up to x to the n forms the basis. How many elements are in there? It's n plus 1, right? Because you got to count the constant term in there too. So n plus 1 would be your dimension for P sub n. How about m sub mn? What is that again? In matrices, what dimension do they have? M by n, right? So how many vectors are going to be in a basis for that? Think about if you're going to write down an m by n matrix, how many spots do you have to fill in? M times n, right? I got to fill out every single entry, right? I got to go across the rows and down the columns, right? So again, what would be a standard basis for that? What would you use for a standard basis for m sub mn? Well, that would be how many there are, but what would we use for what would you use for a standard basis for that? Was it? Yeah, one in each spot and zeros everywhere else, right? And how many of those matrices would you have to use? M times n. So the dimension would be m times n. All right. How about this next example here? It says, what's the dimension of the subspace, or the solution space, if you will, of the homogeneous system associated with this matrix? That seems like it got a lot more complicated. Sounds like it got a lot more complicated. But it's not that bad. If you were trying to write down the solution space, if you're trying to write down the set of all solutions to the associated homogeneous system for this matrix in reduced row echelon form, what would you look for first?
Is it just all the non-zeros?
What do you mean?
Would you just find all the non-zero entries and count them?
Not if I'm going to write down the solution. I want to write down the solutions first. Yeah. What do I look at for solutions? Just not the pivots, but the other ones, right? Those are the ones that are going to give you the free variables, right? Okay. Where are your free variables here? What columns are the free variables? Yeah, 4, 6, and 7, right? So you would have x4 as a parameter, right? x6 is a parameter. x7 is a parameter, right? What's x5 in terms of those parameters? What row am I going to look at to figure out what XR is? Here you go. Yeah, it's this row, right? This is the row I'm going to use to figure out what X5 is. Remember, there's the understood zeros down this column. It hasn't been that long since we've done these. Okay. Minus 2s, minus 60, right? For your X3, you would get okay. Okay. Your X2. There we go, negative 2r plus s, good. The next one. Cool, good. Remember, we're just moving these over to the other side, right? We're solving for where we have the coefficient of 1 on those variables. Like I said, it hasn't been that long since we've done these. Okay. Remember, we also wrote this in parametric form. You can pull out the R, pull out the S, pull out the T. What's getting multiplied by the R? Good. And 3, negative 2, negative 1, 1, 0, 0, 0 there for the R's, right? What about the S's? Good. And the T's. Good. All right. So remember we wrote that in that parametric form? That's what we called it before, was a parametric form, right? Notice that what this says is that every single vector in the solution space can be written as a linear combination of these three vectors, right? Every single vector in this solution space can be written as something times this first vector plus something else times the second plus something else times the third. Are these three vectors linearly independent? Look at the fourth, look at the sixth, and look at the seventh components of the vectors. Are they linearly independent? Can I get this one from those zeros? Can I generate this one from those zeros? No. Can I generate this one from those zeros? No. Okay, so are they linearly independent? Yes, that's what it means to be linearly independent. Linear independence means that I cannot write one of the vectors in terms of the others, right? They are linearly independent, right? The first vector cannot be written in terms of the other two. The second vector can't be written in terms of the first and the third, and likewise the third one. That's what it means to be linearly independent, right? Each vector is independent of the rest. And again, like I said, I can look at that easily by looking at, I can't generate a 1 from zeros. Yeah. So this set of three vectors is linearly independent, and it spans the solution set. If you have a set of vectors that's linearly independent and it spans, what kind of a thing do we call it then? A basis, right? So this basis has three elements in it. So what's the dimension of the solution space? If the basis has three elements, the dimension is 3. Yeah, so that's the answer to this one. The dimension of W here is 3. So notice here the dimension of the subspace is the same as the number of free variables we had, right? The number of pivotless columns that we had.
Is there a situation in which that dimension would not just be the number of free variables?
No, it's always the number of free variables.
Oh.
Yeah, that number is always the number of free variables because that's how we get our parameters. Yeah. We're going to have a name for that when we talk about matrices here in a little bit, when we start doing spaces associated with matrices. Yeah, you're exactly right. It's just the number of free variables there. Okay, cool. All right. Anyway, when we're doing dimension of a vector space, the important part is to note that we find a basis, we count the number of elements in the basis, that's the dimension of the vector space. Again, because they all have to have the same size. All right. So this next theorem is what we're going to use to do the next couple of problems here at the end, the next couple of examples. We refer to this as the plus-minus theorem. We've already said that a basis for a vector space is a maximal linearly independent set and a minimal spanning set. Right? It's the biggest possible set of vectors that you can form and still have it be linearly independent. It's also the smallest set of vectors that you can form and still have it span. So that's where this plus-minus idea comes from. If you start with a set of vectors that's linearly independent, and you find something that's not in the span, if I throw it in there, then it's still linearly independent. Okay? What I'm saying there is that if you start with a set of if I have a linearly independent set that doesn't span, then it's not a maximal linearly independent set. Bases are maximal linearly independent sets. They also have to span. If I find something that's not in the span, then it's not big enough. I can make it bigger. Okay? That's what the plus part is. The minus, of course, has to do with span. All right. This should make sense from a concept standpoint. Remember, linear independence means that I cannot write one of the vectors in terms of the rest. Well, if it's not in the span, then I can't write it in terms of the rest. Right? So the idea behind this would be, let's suppose that I throw this vector in here, and it is linearly dependent. Let's say I throw that new vector in there, and it is linearly dependent. What is our definition for linear dependence? When we're talking about linear dependence or linearly independent from the definition, what special linear combination are we trying to look at? A linear combination that gives us zero vector, right? So if it's linearly dependent, then there exists, we'll say C1, C2, Cn plus 1, not all 0, so that I'm going to assume my S is full of a bunch of W vectors. I didn't write it down, but let's assume that it's full of a bunch of W vectors. So let's say we have a linear combination of all the W's and the V that gives me the 0 vector, and not all of the constants are 0. Okay? So that's what we would get if we assume that the set is linearly dependent. I would have to have a linear combination that gives me the 0 vector where not all of the constants are 0. That's what it means to be linear. That's the definition for linear dependence. Right? Just going from the definition. Either this C sub n plus 1 number is 0 or it isn't. Those are your two choices. It is 0 or it isn't. What happens if it isn't 0? What can you do? What am I allowed to do with a number when it isn't 0 that I'm not allowed to do with it when it is 0? Divide. Good. If it's not 0, what can I do? What can I solve for? V, right? I can move everything over to the other side and divide by C sub n plus 1, right? There should be a minus sign. If c sub n plus 1 isn't 0, then I can solve for v. But what is it that we're assuming about v? Look at the statement of what we're trying to prove. What are we assuming that about v? It's not in the span. What does span mean again? The span is the set of all So that's if we're trying to make a matrix and put it in reduced row echelon form. But as far as span goes, what's its definition? What do you try to do with the span? I take all the vectors and do what with them? I make well, the matrix is how I would check if I have a bunch of vectors, right? But if I'm just trying to think about how we make a span, what's the name of this class? Linear algebra. Okay, I'm going to do the span and do a set of linear combinations, right? So the span is a set of all possible linear combinations. What did I just write V as? A linear combination of the W's, right? Isn't this a linear combination of the W's? Okay, so what would this say about V? If it's a linear combination of the W's, that it's in the span. But what are we assuming about V? It isn't, right? So if we have this would mean V is in the span of S. I'm assuming again that these W's are coming from S. Span is a set of all linear combinations. I have written V as a linear combination, so it's in the span, but we assume that it's none, right? Okay. What led us down that bad path? What did we assume about C sub n plus 1? It's not 0. So what does C sub n plus 1 have to be? 0. Now that gives us C1W1 plus C2W2 plus CNWN is the 0 vector, right? But what is it that we're assuming about S? Yeah, so what we're assuming about S, we're assuming that it is what? What are we assuming about S? Linearly independent, right? So what does that mean that all of the C's have to be? 0. Yeah. Oops. Since S is linearly independent, we now have C1 equals C2 equals Cn equals 0. So what about our assumption up here? Is that set linearly dependent? No. Right? So that tells us that our supposition up there is false. In fact, I didn't even need to make it. We actually really proved this directly. But we get to the point where we add a new vector. This is still linearly independent. So the idea here is that if we start with a linearly independent set that doesn't span, we can make it a bigger linearly independent set and keep adding things to it until I get big enough to make a basis. So that's actually the second part of the theorem, where it says that the second part of the theorem here says that if I have a vector in S and I can actually write it in terms of other vectors, then I don't need it. Right? I can throw it out and still get the same span. Right? So the idea behind that is the following. Again, let's use the W's in there for representing the S. So let's say our S is W1, W2, Wn, and V. Just for notation's sake. If we start with some vector in the span of S, how can I write X? Say X is in my span, how can I write X if it's in the span of S? Yeah, the linear combination of the W's with a V possibly in there, right? So I can write this as a C1W1 plus C2W2, CNWN plus CN plus 1V. For some constants that are in whatever they are, for just for some constants. What are we assuming about V now again in this particular example? The linear combination of the other vectors, right? The idea here is that the statement says that we don't need V to generate the X. Right? It says that we can throw out the V and still be able to generate all of the same vectors that we could have to start with. What do we need to do to throw out the V now? It's not a tricky concept. We've been doing it since Algebra 1. What do we need to do to get rid of the V? I'd use a different sub word. Not subtract, but substitute, right? I can just take it and plug it in, right? I can just take this thing that we just wrote V in terms of the W's and plug it in and rearrange, right? You would have what? You'd have a C1 plus D1, Cn plus 1, W1, a C2 plus D2, Cn plus 1, W2, all the way out to Cn plus Dn, Cn plus 1, Wn when we rearrange. Substitute, distribute the Cn plus 1 and regroup. That's an Algebra 1 thing, right? Didn't do anything fancy. So now I have that X is in the span of the smaller set. All we're saying here is that if I've got an extra piece of information that I don't need the V to generate the span. I can throw it out. The whole idea about this, again, is we're trying to create bases. Right? I want to be able to write every single vector in my vector space uniquely in terms of a given set of vectors. That's the idea here, right? I want to write it uniquely as a given set of vectors. So I want to throw out extraneous information I don't need because that may not give me uniqueness. In the previous part, I need to make sure I add all the information I need so that I get existence. That's the idea behind this. All right. So what does this tell us overall? So that's the next part. What does this mean? It says that every linearly independent set can be expanded to form a basis. And every spanning set can be reduced to form a basis. That's what the plus minus theorem allows us to do. If we've got a linearly independent set and it's not big enough, we can keep adding vectors in there until it does get big enough. And the way we're going to pick how we add those vectors in there are to pick things that aren't in the span to start with. Likewise, when we do reducing a spanning set, we'll just throw out the ones that we don't need. We'll just check which ones are already in the span of the set of a smaller set of vectors. So let's do this by example. This first example, and again, the problem numbers don't make any sense because this doesn't match up with this textbook we're using, is this one asks us to expand to form a basis for R4. Okay? All right, so here's how we're going to do it. We already know how to check if something is linearly independent or if it spans, right? What do we do to check if something is linearly independent or it spans? A set of vectors. What do we do? Make a matrix, right? So that's exactly what we're going to do here. Here's the idea. We're going to take this and put the first vector down column 1, the second vector down column 2. And then we're going to add on columns. We're going to add on vectors that we know for a fact span. What set of vectors in R4 do you know for a fact will span R4? Yeah, 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So we're going to add those vectors in here. 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. I've guaranteed that I've added a spanning. I made a spanning set here. Okay. What we're going to do is we're going to throw out which ones we don't need. Okay, that's the idea. How are we going to determine how to throw out which ones we don't need? What do you think we're going to do with this matrix? Row reduce it. Yeah. Okay. So let's see if we can do that real quick. I again will do this in R since I can do it in R faster. Then type it on the calculator. If I can find my example. And then expand this so you can actually see what's going on. All right, so the first vector was 1, -4, 2, -3, and the second vector was -3, 8, -4, 6. And then we'll put in 1, I wonder if it would do that way. 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And then let's make sure my matrix looks right. Does that look right? Okay. And then row reduce. are we going to be looking for then to figure out what we want for our basis? What columns do you think we should pay attention to? Say it again, Devin.
The free variables.
The free variables are the ones that give us those solution sets, right? The space. We need how many vectors in our basis for R4? 4. So now I don't want the free variables here. I want the one with the pivots in them, right? So I'm going to go back to the original matrix and pick out the columns that have the pivots. So which columns have the pivots? 1, 2, 4, 5, right? So I'm going to use column 1, column 2, column 4, and column 5. Okay? So going back over here, I don't remember what we had. We had 1, 0, 0, 0, 0, 1, 0, 0. Some other stuff here that wasn't a pivot, right? 0, 0, 1, 0, 0, 0, 0, 1, and then some stuff here that wasn't a pivot, right? So our basis for R4 here then will be your first column, your second column, the fourth column, which corresponds to 0, 1, 0, 0, right? This one here. We're going back to the original and picking out the corresponding columns. And then the last one will be 0, 0, 1, 0. Where did my page go? That was weird. My problem disappeared. Why does this hate having a PDF in here? Where did it go? The whole page just died. That was weird. Anyway. All right, so again, you have the problem on your paper. Again, here was the process. We took the set that we wanted to expand. We added on vectors that we know for a fact span. In particular, the standard basis for R4. We row reduced and went back to the matrix that we started with that corresponded to, picked out columns that correspond to the ones that have pivots. Because those are the ones that are going to form the linearly independent set and span. I don't want to use the ones that don't have pivots, because remember the things that don't have pivots are the ones that I can write in terms of the other vectors. Right? Okay. In particular, let me go back to R. Bless you. Let me go back to R real quick here. In particular, I can write the vector 1, 0, 0, 0 as -2 times this one plus or minus this one. I'm getting those numbers from here, right? -2 times the first minus the second will give me 1, 0, 0, 0. That's what that says in the reduced row echelon form. Okay? So I don't want to pick these columns out because those are the ones I can write in terms of the other. Okay? In fact, this one tells me I can do negative the first minus a third the second minus 4/3 the fourth plus 2/3 the fifth gives me 0, 0, 0, 1. And you can check those. Okay. So again, create your matrix, row reduce. Go back to the columns that have pivots that correspond to them. So I want to pick out these 2 extra ones. Okay. Don't use the columns that came out of your reduced row echelon form. That's not right. Go back to the original that correspond to the columns that have pivots. Okay. All right. Let's do the last one. The last one, it asks you to find a subset of those vectors. 3 plus x minus x squared, 2 plus 3x squared, 1 plus 3x minus 15x squared, x plus 2x squared, -3x plus 9x squared. This one asks us to find a subset that is a basis of P2. How do I know that this is, without doing any work at all, besides something that you learned back when you were probably 3, 4, 5 years old, without doing any work at all, how do I know that this is not a basis? Say it again. There's 5 elements in there. How many elements is in a basis for P2? 3, right? If it's going to be a basis, it can only have 3 elements. That's it. It's the only choice you have. This has 5. So I don't have to do any work besides, like I said, do something when you're like 3, 4, 5 years old. Be able to count to 5. Okay? Right? I got to count. But that's it. There's anything else that I have to do that's any work at all, right? There's 5 elements in there. That's bigger than 3. So it's too big. Okay? So what do you think we're going to do to reduce this down to a basis? Or pick a subset out that gives us a basis? What do you think we're going to do? Make a matrix and row reduce. Hey, look at that. That seems familiar. So remember when we make a matrix from the polynomials? It doesn't matter what order you make your columns in, just as long as you're consistent, right? So if I do constant x squared in the first one, I may need to make sure I do that all the way across, okay? The order doesn't matter in which you do it, just make sure that you're consistent all the way across. So your first column would be 3, 1, negative 1. If I do it the way it's written, what would the next column be? 2, 0, 3, good. The next one would be 1, 3, negative 15. 0, 1, 2, 0, negative 3, 9. Oops. Right? And then we'll row reduce. So again, let me get into something that actually I can row reduce in easily. So 3, 1, negative 1, 2, 0, 3, 1, 3, negative 15, 0, 1, 2, 0, negative 3, 9. Assuming I typed that in correctly, that's what we get. So going back again, how do we figure out what we're going to use for our bases? Yeah, pick out the columns that have pivots and go back to the original that we worked with, right? So what columns in the original are we going to pick out? 1, 2, and 4. So the polynomials that correspond to 1, 2, and 4 are what? Okay, so the 3, 1, negative 1, but as a polynomial, it's 3 plus x minus x squared, right? That was the polynomial. The next one will be Yep, 3 plus 3x squared, and the last one will be, yeah, the x plus 2x squared. Yeah, good. And that would be our basis then for the P2. Process is the same for both. The only extra step for expanding a linearly independent set is that we have to add on a spanning set that we know. Right? But once we add on the spanning set that we know, we're basically just doing a spanning set and reducing it to a basis. So both problems are the same. There's just an extra step when you want to expand a linearly independent set to a basis. You got to start with a spanning set that you know. Questions on that one at all? All right. So the next topic is talking about all of this stuff, but in the context of looking at a matrix. Not that we haven't been looking at matrices to start with, but what we're looking at are spaces associated with a matrix. Yeah, exactly. Well, I was going to say bases, and so then I got spaces instead of spaces. All right. So let's see here. See if I can not lose my writing here. All right, so if we start with any M by N matrix, doesn't matter what that M by N matrix is, we can form 3 different spaces out of them. Well, we can form more than that, but there's 3 that we start forming that are relatively straightforward. One we've already done. All right, so we have row space, column space, and null space. And this goes along with section 4.6 of your book. So 4.6 of web assigned as well. All right, so all the spaces that we're going to generate, we've talked about different spaces that we've generated before. All of them that we generate are going to be linear combinations of certain vectors, okay? So for the row space, what we're going to think of is each of your rows as an individual vector and then generate all of the linear combinations, okay? So the row space of A is just the set of linear combinations of the row vectors of A. Treating each row like it's a vector. Look at each of those, make a linear combination. That's how you're going to get the row space. Where does the row space live? Well, if you think about treating each of your rows as a vector, how many components does it have as you go across? If it's an M by N matrix, how many components do you have as you go across? The number of columns, which is N, right? So this will be a subspace of Rn. What do you think we're going to do for column space? It's a set of linear combinations. It's the span of the column vectors, or the set of linear combinations of the column vectors. Where does this one live? Rm, right? Because column vectors are going to go down the rows, so each of them will have M components. So this will be a subspace of Rm. The null space is one that we've already done. We just haven't called the null space before. Okay. This is just the solution space. That was weird. The brightness just dimmed on my. This is the solution space of the associated homogeneous system. Where does this one live? Well, if my A is M by N, what size does your X have to have? So if it's M by N, what size does X have to be? N by 1, right? It's a column vector, right? So this is going to be a subspace of Rn. All right. We've already found null spaces before. We just haven't called it that. We just did that earlier today, didn't we? When I wrote down the solution set to that matrix that we had. Right? We've done null space before. We're just giving it a different name. All right. So we'll talk about how we can work with row space and column space and what that tells us on Wednesday. But this should get you, the basis stuff that we did should get you through the homework that's due on Wednesday and the web assignments due tomorrow. We'll finish this stuff up on Wednesday. So have a good one. Say again, Ben?